So in this talk today, I want to propose certain operators on tropical points of cluster algebras. The description is very simple, so I wouldn't be surprised if they pop up somewhere else. So please let me know. And from my point of view, they entered the picture when studying crystals due to Kashiwara or Lusztig. And so that's why, so they resemble the crystal operations. And well, let's see. Okay, so let's start with cluster algebras. So for this, we take a Q, a finite quiver. We don't allow loops or two cycles. And in physics, these quivers might be, for example, the quiver associated to BPS states. So don't ask me about this, but just if people come from physics. You might think of it like this. So to such an object, there is a cluster algebra associated. By Fomin and Selevinsky. And this is a subalgebra of the rational functions on n variables, one variable for each vertex in the quiver. So these AIs are the initial cluster variables, and we have one initial cluster variable for each vertex in the quiver. So this cluster algebra is given as recursively doing certain combinatorial rules, applying them to the cluster variables. So we start out with a set of initial cluster variables. And then there's a combinatorial rule, which depends on the quiver, to produce a new set of cluster variables. And this process can be iterated, possibly infinitely many times. And what we obtain from this is called the cluster algebra. So in fact, this process depends, the blue arrows depend on the vertices. So for each vertex, I get a blue arrow, and then I can apply another vertex. And I do this until I don't get new elements anymore. And it's a fact that this is lives inside of the Laurent polynomial ring of the initial cluster variables. The Laurent phenomenon. Due to Fomin, Selevinsky. So this blue process we call a mutation process at the vertices of the quiver. So that means for our initial datum was this finite quiver and a set of initial cluster variables we obtain via mutation at a vertex K. A similar datum, but mutated, consisting of a new quiver, Q prime, the mutated quiver, and mutated cluster variables. Okay. So how does this look in detail? There's an explicit recipe describing these mutations. And on the quiver, it looks as follows. We replace, also first we change the cluster variables. We replace the variable AK by a new variable, AK prime. Which is given by this formula. We take the product over all ingoing errors into the vertex K. And we take the product of all these cluster variables attached to these vertices, or these cluster variables HJ attached to the vertices, which have errors going towards K, plus the product of the same thing for outgoing errors from K. So the two packages, like where we go from K, we take the product, where we go to K, we take product, and then we take the sum and divide this by the old cluster variable, and this is the new cluster variable AK prime. So this is what we do on cluster variables, and then on the quiver, the following changes happen. First, we add transits. Through K. Then we reverse all errors. At K. And finally, if it happened to produce 2 cycles, we remove them. And this is the combinatorial formula, which produces the cluster algebra. Let's see this on an example. So we have, say we have 4 variables, A1 to A4, so the quiver has 4 vertices. And let's pick this quiver here. And we want to mutate, say, at vertex 2. Well, let's mutate at 3. More interesting. So first we need to replace the variable by a new variable, A3 prime. So I said we take the product of all incoming vertices, so that's A1 times A4, plus the product of all outgoing, that's just A2. Here the outgoing A2, the incoming was A1, A4, and divide by the old cluster variable A3. Now about the quiver, let's first draw the old quiver. The rest of the cluster variable stays the same here. And the first step was to do our transits. So transits, by this I mean Here we go from A1 to A3 prime to A2. So the transit goes from A1 to A2. And similar, we get a transit from A1 to A2. Then, okay, then we have done our transit, then we have to reverse the arrows at K. And now we have to remove 2 cycles. But there's none, so we're done. Okay, so this is how this process works. So what do we obtain from this? The easiest non-trivial example is the A2 quiver. Let's call A1A and A2B, and then we mutate at A. So we replace A by the ingo product of incoming arrows. That's nothing, that's 1, plus outgoing is B divided by A. We just turn around the arrow in this case, there's no transit, and B stays. Now we can, so we obtain AQ is the algebra generated by A, B, and now we have a new cluster variable, 1 plus B divided by A. So we record this. Then we mutate at the second vertex B. For the quiver, it's simple in this case because just the arrows flips around every step. And for the cluster variable, the first one stays. And the second one is replaced by 1 over B times product over incoming plus product over outgoing. So that's, again, 1 plus B over A. So we can reformulate this as 1 plus A plus B divided by AB. Then we can mutate on the first vertex and obtain, well, after multiplying it out, 1 plus A over B towards 1 plus A plus B divided by AB. So we recall this term as well, 1 plus A over B. Then we mutate on the second vertex. And obtain A again, if we multiply it out. So there's nothing new. We can again mutate on the first vertex, but then we obtain just B to A, the quiver, which is the opposite quiver from the initial quiver. But we are done now generating the cluster variables because our terms are symmetric. So this is our cluster algebra in this setup. But usually it's infinite times we have to repeat this, so it can obtain a complicated thing. So this is what I just explained was the A cluster algebra, and so when we have A, there's also X, and there's also a way to formulate this geometrically. So let's say T is the spectrum of the Laurent polynomial series in our cluster variables from one cluster, from the initial cluster. Then this embeds into the spectrum of the cluster algebra. Let's call this space A. And there's a dual phenomenon. So there's an X mutation, which gives us a dual torus. So this is a slightly different rule to compute the mutation. And let's denote the variables by X. And furthermore, there is a nice map between these two spaces, A and X, the P map. So I mean, tropical, so it's a regular map, and tropically in one for one torus for one seed, it's just multiplication by the B matrix, the matrix associated to the quiver. So now there is a nice conjecture by for Goncharov, which says that there are nice spaces, should be nice spaces in these spaces, in these cluster algebras, which are parameterized by tropical points of the mirror of the, so the A basis should be parameterized by tropical X points and vice versa. And so this is in a lot of cases proven due to a Gross-Hacking-Keel-Kontsevich. And so there's a nice basis, canonical basis. For the cluster algebra, B, which is parameterized by tropical points in the X space, the tropical X points. Or more precisely, like it's parameterized by a certain cone of tropical points in the X space if we have frozen vertices. Frozen vertices are vertices where we're not allowed to mutate it. So the tropical points, this is the co-character lattice of our torus. And then if you have frozen vertices, there is a certain function, f, which is called Landau-Ginzburg potential function. And this cuts out a cone in the X, tropical X points, which parameterize the basis of the A cluster algebra. So tropical point corresponds to a function in the basis. And this is true if P, the P map, so the P map in, let's say tropically is multiplication by the B matrix, has full rank. And each frozen vertex, so frozen are just a subset of the vertices where we're not allowed to mutate it. I said we can mutate at any vertex, but in frozen vertex is forbidden. And we want here, or we ask for the condition in order to have this this theorem working that any frozen vertex has an optimization. I will explain a bit more about this. It's a special sequence of mutations, which I'll elaborate on in a second. And the mutable part, so this is the non-frozen part of the quiver, should have a reddening sequence. I'll also say more about this in a second. Okay. So there are some technical conditions, and under these technical conditions, there's a nice basis, which is parameterized by the tropical points in the mirror. So what are a little bit about these technical conditions, maybe? So the first condition says that the P-map has full rank. So by this, I mean the tropicalization of the P-map is given by sending a point A to B times A, BQ times A, where BQ is the matrix associated to the quiver, which encodes the errors. The second condition was that each frozen vertex has an optimization sequence. So frozen means mutation is prohibited. And optimization sequence means it's a mutation sequence, so a sequence of vertices, such that after we mutate, there is no arrow pointing towards this frozen vertex V. So an optimization sequence for frozen vertex V is optimization sequence is a sequence of vertices, a sequence of mutations. Say μ1 to μk, such that in QS no arrows points towards V. So finally, a reddening sequence. This is we can say it's an optimization sequence of the principal extension of the mutable part of the seed. So we cut off the frozen vertices and then we augment the quiver by arrows pointing outwards to a new copy of vertices, and then we optimize them simultaneously. So reddening sequence is a mutation sequence S, it's like this optimization sequence of the non-frozen part, such that all vertices in the mutated quiver are optimized after when we augment the mutated non-frozen part, as in this example here. So I mean, so the original quiver is the white quiver here, and we say there's one frozen vertex, we cut the frozen off, and we obtain the white quiver downstairs here, and then we add a copy for each vertex, an arrow pointing towards this vertex. So this is our new quiver with frozen vertices, and then the reddening sequence has the task to turn around these blue arrows. So all frozen vertices should be optimized after applying the reddening sequence. Okay. So now we are all set to define operators on the tropical points. So let's choose a frozen vertex. In the quiver Q. And then we obtain operators on the tropical X points, which are also defined on the cone cut out by the potential function associated to this frozen vertex. So let's give them a symbol. The operators, let's denote them by F V check. Just can't write there right now. And I say they are like crystal operators because in certain situations, they are crystal operators. And they're defined as follows. So it's very simple. So we find an optimization sequence, mutate there, then we basically add just the unit vector at the frozen vertex and mutate back. If we work in X cluster variables, we apply the PMAP before adding the unit vector. So the same game can be played in A cluster. Usually I work this out in A cluster, tropical A cluster coordinates. Yeah. So we take the point X, apply an optimization sequence S. This here is just tropical mutation, the application, tropical X cluster mutation. So I didn't write down the formula. I wrote down the tropical A, the A cluster, the geometric A cluster transformation, and this is a similar thing. So we first mutate along an optimization sequence S. Then we add the unit vector at the frozen vertex, and in X cluster variables we first apply the PMAP. And then we mutate back. So very simple thing. So for example, what one can do is the following. Let's look at the A2 quiver for a second. And then we take the principal extension, or co-principal, I guess, in this situation. So we add one copy for each of the vertices, and we add errors into the copied vertex. And then we can apply this definition above and obtain two operators. In fact, we obtain four. So because there's always like the dual principle. So we can either go to an optimized seed or co-optimized seed. So there are four operators. And well, what do they do? So after I compute this, the first operator, so first of all, like the second operator are trivial because I said the dual version is we go to a co-optimized seed, and yeah, I mean one of the either co-optimized or optimized is already happening in the first seed because we take the co-principal extension. So the operators are trivial; they always act just on the frozen vertex. And the other operators, where we first have to apply our reddenings or greening sequence in this case, has a more complex, more complicated structure, and there are several options of vectors we can add up to this application of the PMAP. They look as follows. So for the first vertex, the first frozen, the vectors are either just adding one at this point, or we follow one path along the arrow, or we apply here. So these are the three vectors for the first operation, which are relevant, and similar for the other operations. This is a small example. So let's give a more complicated, more larger example. And I prepared this in Sage, but I have Sage on a different device, so I just prepared this. So in this situation, we have a quiver associated to a double Brouwer cell in a reduced word. So we take the standard reduced work here, 1 to 1, 3 to 1, 4, 3 to 1 of A4. So here's the quiver displayed. It's a little bit, I mean, it's some algorithm which produces it, so it's a little bit unpretty. So I put it into a Keller's applet and shaped it by hand. And then it looks as follows. Okay. So this is the same quiver. I just reshaped it a bit, and then there's a shift by 1 because of technical reasons with the vertex labels. And so the frozen vertices are marked blue here, and the mutables are the red vertices. So here we have, so note, I mean, the thing we did before with the A2 quiver can be done for any quiver. So I mean, as long as we have a reddening sequence, we can take the principal extension and obtain, so the reddening sequence in this situation is our optimization sequence, which simultaneously optimizes all frozen vertices. In particular, this implies that the crystal-like action obtained by the principal extension is commutative. So and in this situation, it's different because we see our frozen vertices, they interact. So they cannot be simultaneously optimized. And that's why we get a little bit more complicated action here. And I asked the computers, I asked Sage to compute what we get. So, result is as follows. So these are the vectors we obtain. So there are 4 frozen vertices, so we should obtain 8 set of vectors, 4 for optimization and 4 for co-optimization. And they look as follows. If you look precisely at the coordinates we have here, I mean, like the order structure is pretty similar on all of them. But if you look at the coordinates, we can see how they reflect on the right-hand side. So the optimization vectors, they correspond to the level lines here. We see like we see these 4 vectors, for example. They are this vector and this vector, this vector, and this vector. And this corresponds to the crystal structure on the string cone due to Kashiwara's embedding theory. And the other 4, they lie diagonally here. And the resulting operations correspond to the crystal structure on Lusztig data. And in general, this is described by a crossing formula due to in joint work with Gleb, Koshevoy and Schumann. And if one can show that under certain change of coordinates, this the crossing formula can be reformulated in cluster coordinates, such that the vectors by which the crystal operators act have disappearing as here computed by the operation we defined via applying first this optimization sequence, then adding one and come back. And of course, this is not commutative, this crystal. And we can see this in some sense on the quiver because the frozen vertices interact. The frozen vertices correspond to the simple roots, and in the sense, in the way they interact in the torus embedding, we can see that here they interact in the quiver. So they cannot be simultaneously optimized. We have the following questions. So how to find those optimization sequence? I mean, if we are given the optimization sequence, we can compute the action. But in general, if somebody gives us a quiver, we don't know how to find this optimization sequence a priori. So this is some problem I would like to solve. Another problem is how to compute these operators directly without, I mean, even if I have an optimization sequence, I would like to compute them directly without applying the optimization. And this is the spirit, how it should look like. We write the Landau-Ginzburg potential function associated to the co-optimization, which is an S polynomial. We write this in terms of the cluster coordinates in the seed we are in, and consider the set of monomials which appear in this function. And let's assume that they are precisely the vertices of their convex hull, which is not always the case, but let's assume this for a moment. And then the formula should look as follows. If I apply the crystal operator to a tropical point x, then I get x plus something, and this something is a vector rx multiplied by the p-map if I want to work in x cluster variables. If I work in a cluster variables, I don't have to apply the p-map, but I need to apply the p-map in order to compute the scalar product on this here, which is now the standard scalar product. So what is the Rx vector? The Rx is one of our monomials, or one of the exponents, and it's the maximal one, such that the scalar product with x is maximized. So I take all possible scalar products of the exponent vectors with x, and then I look at which guy maximizes this, and I take the maximal in terms of I order the monomials by degree, by multi-degree, and I take the maximal one, and this is the vector which should act in the seed on this tropical point x. And furthermore, all monomials in this situation should show up as a crystal vector. So this is the spirit. And then this is also what's happening in the example we had here with the type A quiver, type A double Brouillard cell. So this is also a consequence of the crossing formula, that this is what happens. Now, let's do maybe two more examples. So this is the same thing as we have just seen in type A, but in type D. So we have here a quiver of a double Brouillard cell for D4. I cut off all frozen vertices besides the interesting one, so the most complicated one. So the other root operators, they are not visible in this quiver anymore. And compute the vectors with which our crystal operator acts. And this looks as follows. So this is in this situation the lattice of vectors. It's a little bit overlapping. And here something happens. So these conditions which I noted that the exponents should be their linear hull so here's one problem occurring, that there is a vector which has which cannot be hit by this linear rule. Yeah, we have this linear rule. We take the scalar product of the vectors with x, and we choose the maximal one. And here there's a vector r, such that r plus ek, this is the kth unit vector, and r plus 2 ek all appear in the exponents of the expansion of the f polynomial. So is it even possible to choose r plus ek, one might ask? Yeah, because yeah, I mean, from our rule before, that wouldn't happen, so it wouldn't occur. But in this situation, if we use the optimization method to compute the crystal, we see that this actually can occur, and it can precisely occur if and only if this vector Rx, which is the middle vector, is the problematic one, which might not occur. But it does occur, and precisely if it maximizes the scalar product and does it in a way such that it's almost like just barely adventurous for the neighboring vector. So there's like an offset of -1. And then if it's so if this value is -2 or -3, then indeed the lower the vector r, the vector r acts, and the vector r plus ek acts if and only if we have this offset -1.
Apologies, Volker. I think we slowly have to wrap up because there's a practical constraint at ERCS regarding the coffee break. So do you think you might be able to finish in about a minute or so? Thank you.
So there we see like a little bit more complicated structure when the vectors occur like this. And let me give one more example of this shape. So here we have a quiver with multiple errors. So this is not related to Lie theory. So we have maybe physicists in physics, this appears the quiver. So we have 3 errors, then 2, and this augmentation by the frozen. In this situation, the possible vectors look as follows. So this is the lattice, but I marked it a little bit, I drew it a little bit nicer. And the linear action would only be able to choose this vector, this vector, this vector, this vector, so the linear rule, and this vector. And the other rules, the other vectors are chosen in similar way to the case above. So with these offsets, so this has offset -1, -2, -3 on the corresponding vertex, which increases here in the vector. Yeah. So that's it. Thank you.
Thank you very much, Volker. Let's thank the speaker. Are there any questions? So in particular, if ERCS has questions, please let us know.
have a question. Can you hear?
Yes.
So if we consider our favorite, not principal extension, but if we consider triangle product with A2 quiver, then we will obtain a non-commutative crystal structure.
Sorry, 1 second. I somehow turned my audio a little bit too silent. Let me try to turn it up. Okay, come again.
Yes, so if we consider, so you started that if you consider principal extension, then we obtain crystal operation with commuting. So all crystal operation will commute for all frozen. But if we consider triangle product with A1 quiver, so we consider such principle, such not principle, but triangle extension of the quiver, then it would be a non-commutative, I guess. Did you have some examples? Computing?
I don't know. I think somehow, I don't know. Somehow I thought about this, but I think somehow my feeling is it should be commutative, but we should just check. Like, I mean, we can just afterwards just ask the computer, I guess. He said, because it seems like the principal extension and the triangle extension are somehow the two canonical extensions. So I don't know. So they always exist. So I think it should be commutative, but I don't know.
Because you cannot find in the triangle extension, you cannot find simultaneously optimal sequence for all vertices. So that will be different.
Yeah, okay, but maybe that's not necessary, right? I mean, I don't know. Yeah, I mean, we should check. Yeah.
Okay, check. Wait.
Just because it's canonical, I was thinking that maybe it's commutative, but I don't know.
So are there any other questions? Also from the online audience, of course. Let's thank the speaker again, and